you, Judy. Yeah, I'm sorry I'm not able to be there in person. I really enjoyed my time there last year, so hopefully I can make it next year. But I'm very excited to be here to talk to you about vector embeddings, and to your point, Judy, about not not necessarily feeling like you belong there, or hopefully this talk will bring this back down to earth. And I think even if the term vector embeddings is scary, we'll dissect that and get to a place where I think you'll hopefully appreciate that it is actually about improving accessibility and making this more approachable to everyone. So with that, let me just jump in. So my name's Andrew Sellergren. I'm a software engineer on Google Health. I've been at Google for almost 15 years now, but only on Google Health for the last 5. But during that time, I've worked mostly on chest X-ray modeling, but now that is bridging out and towards lots of other modalities, including pathology, dermatology, beyond just radiology. And I'll actually talk about how vector embeddings are one way of doing that. They are this nice representation that allows us to bridge all these different modalities. So let me start with just my 3 takeaways here that will hopefully come across in the talk. So first, Google Health's mission is to improve accessibility. There's many different facets of this, but first and foremost, we want it to be accessible to everyone. People's health information should be in their own hands, and they should be empowered with it, and they should understand it. Vector embeddings themselves are actually a way of improving this accessibility. So they reduce barriers to entry. And finally, the vector embeddings are also a potential bridge between all these different medical modalities, and paving the way forward into this brave new world of large language models as well. So with that, let's talk first about Google's mission about reducing barriers to development here. So it might seem a little strange, or you might be kind of wondering, what is Google's place in this space? And it's always a little hard to kind of position this with all of our other, some for-profit entities or aspects of our business. And the really great thing about Google Health is that we're not really caught in between all of that. We see ourselves as an enabler. We're not building medical devices. This isn't really a revenue stream. We might be, there's some services that we might be ending up charging at some point, but it's really nominal compared to our other businesses for sure. So we're not looking to maximize that. And most of the tools that I'll talk about today are free of charge. And we're pushing hard to make them more available, easier to use. And so our role here is as an enabler. The case study I'll talk about today is relating to chest X-rays, but I'll also try to bridge the gap to other imaging modalities. I'll dive into some of the technical details just to kind of get our feet wet, but please don't hesitate to stop and ask questions, or we should have some time at the end as well. So with that, let's talk about chest X-ray, which I think you've already gotten a lot of great information about, but positioning this as to, why did we start with AI for chest X-ray, and specifically why vector embeddings for chest X-ray. Chest X-rays are ubiquitous, and they're also relatively inexpensive. So there's about 1 billion, probably more like 2 billion even, or between those two, taken every year. But there is actually quite a shortage of radiologists to read them, particularly in certain areas of the world. So with that, there's definitely an opportunity for AI to intervene to help bridge that gap between the supply of radiologists. That being said, it's still very challenging to develop AI for this. So there's a lot of variability between experts reading this, between sites, between scanners. there's a very long tail of rare conditions that can be visualized on chest X-ray, and also the actual compute and expertise that's required to build these is extensive, right? So the models I'm talking about today are going to be actually. It's funny that this talk has already been dated by a year or two, because the largest models we were talking about as of a couple of years ago for imaging were tens of millions of parameters, and now they're a few billion parameters. And then of course the large language models are hundreds or 1,000 billion parameters, and they also take an extensive amount of fine tuning. So lots of software engineering time on our part, a massive number of accelerators. We're using huge, well-curated data sets, hundreds of thousands, millions of images. And so, this is starting to sound inaccessible, but that's actually kind of the point, is that we as Google want to offload most of this very expensive part of the training, and kind of lean into what we do best, and then allow other people to do what they do best. So we are lacking on the clinical side of things, or the actual ability to apply this in real world scenarios, but we have a lot of extensive experience on the model development side. So to put that in more succinctly, our mission here is to really enable others to train better custom medical imaging models. So we know that we can start with this large foundation model, but the last mile is always going to be taken by the folks in the field, the ones who have the most clinical experience, but possibly less technical experience. And that's okay. We kind of need to reach across the aisle here, and we might have the technical experience, but we very much know that we don't have all the clinical experience. So we have a few clinicians on staff, but we're always having this conversation of what is going to have the biggest impact, and what is going to actually help you all, right? Not clinicians as well as patients, right? We don't want to be getting in the way and proposing things that are far-fetched or not useful. So how do we accomplish this mission? We are talking here about vector embeddings, which will help on 3 axes. So in order to reduce the barrier to entry for training these custom models, we want to do 3 things. We want to decrease the training time, we want to improve the label efficiency, and reduce the model complexity. So the training time, as I mentioned, for our large models takes weeks, right? And that's if you got all the hyperparameters right. But for training a model on vector embeddings, you're talking about 5-10 minutes, maybe. Probably less than that. Some of them we can do in the browser, right? And as a testament to this, last year at the Datathon for Emory, the team that worked with the vector embeddings was able to iterate much faster and train multiple models, multiple goes at this thing, because they were using embeddings. So this is very powerful prototyping framework. Likewise, because it's got all this foundational knowledge built in on millions and millions of medical images, it's quite label efficient. So you might only need tens, maybe a couple hundred, maybe a few thousand downstream images for your task of interest, for your actual clinical setting, in order to get a performant model. So again, this kind of last mile problem where now you have a much smaller model you can train, and you only need, I only need a few hundred images from my particular hospital system, which we know is going to be, that alone is going to be hard to collect, let alone the hundreds of thousands or millions that might be necessary to develop such a foundation model. And finally, the model complexity is also much lower. So if you only have a few layers in your final model, then it is a lot easier to maintain. You've traded a little bit of that by adding this foundation model into the mix, which hopefully we've simplified with this API. But the idea is that the technical complexity for someone who's developing these models is much smaller. So you don't have to worry about, you know, how to train or how to pick hyperparameters and tune this thing. It's much more easy to wield. So as I mentioned before, the method here really is to just lean into what Google is good at and lean into what you all and others are good at. Our role here is to do large scale medical image pre-training. So we're going to offload as much as we can into our compute and our cloud and our data sets, and then hopefully pass things on down the road to many other players who can actually take things the last mile. So the way to visualize this is that we kind of use is a pyramid. So in a traditional model, particularly for chest X-ray, you would feed it into the base of this, and it kind of gradually narrows down into a single task. So in the past, this usually was just classification, say airspace opacity or not, or pneumothorax or not. And in between the layers of this pyramid are layers of your neural network. So could be tens, hundreds, thousands of layers. And at the very end, you have your 1 or 2 layers that are actually doing the classification. But most of the other layers are this kind of foundation that are gleaning relevant features from the image. So our method here, and I'll just go ahead and skip to the good part here. So our method here is kind of to chop off the top of that pyramid, if you will. So the idea is that we've trained this model with a massive amount of data, huge amount of compute, and it might have been designed for certain tasks at the time, but really those tasks are just to improve the actual sort of generalizability of the model, right? We want a model that does really well at understanding chest X-rays. Doesn't necessarily do the best at one particular classification task or one particular, you know, generating reports. But it's kind of a jack of all trades, hopefully. And I'll talk about how we do that. We'll say, you know, how do we design tasks that get us a better model like that? But for the sake of the downstream case, again, we're kind of chopping off the top of that pyramid, and then we're asking folks downstream to just build that top. So instead of having to build the whole pyramid from scratch, you can build just the top. So in a traditional case, you know, where you might need tons of data, tons of compute, now you can actually just plop a few different tasks on top. And again, hopefully it's good at all of these different things. I think I'm doing okay on time, but I'll continue on now. So how do we optimize for learning the best embeddings? And that I'll motivate this and then talk about what are embeddings. But a few things to observe is, one is that as I alluded to before, the upstream and downstream task performance are not necessarily correlated. So if you trained a model only on one specific task like pneumothorax, it's probably not going to be very good at a lot of other different tasks. So how do you design this upstream task that's going to be somewhat guaranteed to do well on all these different tasks? It's really challenging, particularly when you don't know what the tasks are. A great example that we'll get to here is COVID-19. It's literally a task that we didn't know we were training models for back in 2019. So we're trying to future-proof things, and that's a difficult task. We know very generally 2 things about this. One is that contrastive losses tend to be better for this. So cross-entropy loss is your typical classification design task, and also that bigger tends to be better for these foundation models. So we use larger networks, basically as large as possible, the largest possible image resolution, the largest possible data sets that we can get for this. And again, the point is to lean into where we have an advantage that others might not, and then pass on those advantages. I'm going to skip this actually, but this is the original CXR Foundation, and you'll see embeddings mentioned here, which is basically the result of chopping off top of that pyramid. So instead of getting out a yes or no answer from your model, what you get out is actually embeddings. So what are embeddings? Embeddings are just an array of numbers. The best way to think about it is a compressed representation of your original image. So the same way that you can compress a video file, audio file, you might get an MP3 format or something like that, or you zip all your files up into to an archive. We're doing some compression here. We're doing very, very task specific, or at least modality specific compression, but it's compression nonetheless. So we're giving it a task so that it learns all the possible features that might be useful for tasks downstream. It's a bit hard to conceptualize what this is, but with this array of numbers, we can then put it on a graph like this with t-SNE, a method to kind of put it into 2 dimensions. And with any task, what we're roughly trying to do is put things together into the same space, right? So when we want to do classification, we're really just trying to draw a circle around certain parts of certain numbers of images and say, okay, these ones are positive, these ones are negative. So what we're showing here is that when you have a generic network, you start from, say, an ImageNet pre-trained model. For chest X-ray or for some medical imaging task on the left, you don't get very good separation. If you were even as a human to try to kind of draw a circle around all the blue dots or all the red dots and separate them out, it'd be very hard. Whereas on the right, it gets a little bit easier. And that's without having told the model, okay, here's what airspace opacity is. So the idea is with this array of numbers, these vector embeddings, you have this kind of already well-organized space where it knows here's where all this type of chest X-ray go and you can group them in various different ways. And that's essentially all you're doing when you train your downstream models. So I'll try to run through these since I'm a little short on time now, but one thing to point out here is that we get the same performance with several orders of magnitude less data. Up here on the top, you can see that across 6 types of chest X-ray findings, the black line is actually fine-tuning a whole network. So let's say you wanted to start from scratch or from ImageNet and train a model on chest X-ray. You can see that only when you get to, say, 10,000 or more images do you actually get an advantage there. And again, that's going to take days to train and lots of compute and lots of you tuning it. Whereas with even our original CXR Foundation model, you're starting to get good performance well before that and better performance. And then on task-specific things that it's never seen, like tuberculosis, we're already doing better than if you started from scratch. So this was an attempt in early 2020 to say, okay, could we not only predict COVID, but could we predict outcomes from it? So mortality or extensive, long-term hospitalization, things like that. And we could do pretty well with it. So again, this sort of rapid prototyping, quick adjustment to downstream distributions. I'll jump through this too, but again, training with only 40 or so images, you start to get performance that's as good as radiologists on certain tasks. I'll say this data set is relatively easy, so it's maybe overestimating the ability here. But again, similarly here, we only had a few hundred images. This was the beginning of the pandemic, and we got a month's worth of data from one of our partners. And so what could we do with that amount of images? Well, we did the best that we could, to be able to predict ICU admission or ventilation or the need for vasopressors, but with only a few hundred images. So that was pretty exciting. So as I mentioned, we started with chest X-ray, but this is easy to motivate for other modalities like pathology, particularly with pathology where you have these gigapixel images now. So these are even larger and more unwieldy for folks without as much compute as we have. So can we, again, make these more accessible? Taking in a whole slide and being able to determine, things like, is there a tumor there or not? What's the staging of the tumor? And similarly, with dermatology, we found that this approach of using a frozen model with small models trained on top of it, you get good or even better performance than if you were to try to train end to end with a much smaller amount of data. So before I wrap up, I'll tease kind of two things that are where we're going with a lot of this stuff as well. So the other cool thing about embeddings, particularly image embeddings, is that they become this bridge between all these different modalities. So you may have heard the term embeddings in the context of text as well, and there are lots of APIs out there for OpenAI or Google or any of them that embed text. So it's a similar idea. You're getting this array of numbers back for the text that you provided, and then you could do really cool things like look for similar text or kind of do classification on that. The really interesting thing is that those text embeddings are actually quite close to image embeddings, and this is one of those active areas of research that kind of blows your mind, because why? I'm not really sure. You can train models completely separately on images and text, and the embedding spaces are not that far apart. They're sort of linearly, you can bring them together with just linear layers even. So the idea here is we train our massive foundation models for images, and then one of these small models that we can train becomes actually a bridge, an adapter between that image model and a large language model. So back when we did Elixir, this was Palm, but eventually it became Gemini, and it could be done just the same for Llama or for GPT. So you train a few layers and you're just basically teaching this large language model, okay, here's what these embeddings actually mean. And then you unlock all these different tasks down here, which I'll only hint at. Zero-shot classification. You can do semantic search where you search for similar images or bring up something from your huge database that you couldn't have searched for otherwise. You can do things like visual question answering. And we also get into report generation and report quality assurance even. So I'll skip over this since I'm short on time, but this is the technical implementation of Elixir. We saw that we actually, improved by 2 orders of magnitude over the original CXR Foundation, and this is also available freely right now. Zero shot is something that implies that we actually don't train a model at all. We just we sort of pose the classification problem as a question, is there atelectasis or is there cardiomegaly? And we find that we're starting to approach the fully supervised performance on some of these data sets. So again, kind of proving that this foundation model already has all the knowledge baked in that we might need for some of these tasks. And, again, hinting at kind of what's possible. So the ability to kind of chat with your image, which honestly, radiologists don't really want that particular. It's more of like telling you what this model is capable of, asking things like, is there pleural effusion? You can imagine uptraining non-specialists or non-radiologists to be able to read medical images. Report quality assurance, so you pose a particular report and ask, is this correct? If not, give me the corrections to it. Or on the left here, searching for similar images. So show me ones that have a small right pleural effusion, no left pleural effusion. I will just briefly mention that we've extended this to other modalities with pathology as well, again, using whole slide images, the ability to generate text from these. And then finally, what we've been working on most recently is with Gemini. So if you've been paying attention this long, I'll share with you a little secret of our secret sauce, which is that the image encoder here is actually frozen. So we're still using this idea of vector embeddings, and then we're feeding them into Gemini. So even as we kind of go into this, there's this large language model world, this principle is continuing to bear fruit, where we just take we take an image, we compress it down to an array of numbers, and then the model can understand that. And from that, we can do all kinds of things. We can do, we start to get into 3D as well. One of the things that's definitely not ready for prime time, but is something we're actively exploring is 3D foundation models for CT, MRI. So again, where we have this ability to compute over massive amounts of data, huge resolutions, we start to be able to do things like generate reports and unlock all of these things for 3D modalities as well. So I would be remiss if I didn't thank the Mimic folks. Leo, I think, is probably in the audience there. Chexpert. All of these data sets are massively useful to us. It's not as if we're not even training on some of these. We use them a lot as for evaluation, and also kind of to speak the same language as everyone out there who's evaluating on these, to kind of show performance. But we wouldn't be able to do what we do without them and without the support of folks like Judy and others. So thank you so much. And I have 2 minutes, but there's maybe time for more questions if people have.
No. Thanks, Andrew. Questions for him? Okay. At least for the people who did not know anything, were you able to follow what Andrew was saying? Because you've had those words like, oh, I froze this layer, and right? Like okay. There's some nods in the audience, so that's a good.
Hopefully.
Yeah. Okay. Questions? Okay, I have one for you. Could you point people who may try to do some assignment tonight where they can find a notebook to get started? I know since we won't be having you, so you can train a model in 7 minutes on your CPU with this approach, right? It's pretty remarkable, right? So as Andrew does that, I do have sort of like, you know, how can you, and you alluded to this, but most of the tasks we've seen are sort of like classification tasks. Is there a role for embeddings in the era of segmentation tasks for medical imaging?
Yeah, it's a great question. It's definitely one that it's a lot harder. The literature out there is that you might want to look into, or that you can look into to start discovering more of this, is kind of dense embeddings. So when we train, the way that we're training these models right now to do classification or even report generation is not very, is a little bit more sparse, right? I mean, you don't need to annotate every pixel in order to generate a radiology report. So training in this way of aligning with text doesn't do the best for that kind of a task. So we kind of have to rethink things a little bit and redesign those initial tasks, but it is definitely on the roadmap. It's something that we actively consider, and that goes for, segmentation or object detection. Basically, the more we can do to improve those original representations so that they kind of compress in this original understanding of localization as well as kind of general classification, I guess, the better. But yeah, you're absolutely right. They're not quite ready for things like segmentation or these denser tasks right now.
Okay. There's a question also from one of the.
Hi, I have this question that where in the model can we know we need to freeze that, and then after that we should begin to train the other parts?
It's a great question. Mostly you won't have to worry about that. I mean, it can become kind of an academic question of, which layer would you give out? So each layer in the model, starting from the base all the way to the end, will have kind of different understanding of the image. And actually, that's how a lot of object detection works. Is it might take different layers and combine them because it has different sort of windows of the whole image. But for our purposes for this API, there's just one, and we freeze it basically as deep as possible, and you end up with this representation that is, well, it depends, but might be 1,000 or a couple thousand numbers. And those numbers don't mean anything to us as humans, but they have all of these features built in, and you can easily train models on top of them. So hopefully that makes sense, but it's definitely, it can be an open question for if you were training your own foundation model, how would you go about, what layer would you end up freezing?
Okay. Any luck with a notebook or something?
Yeah, I sent it to the chat, but if it's easier, I can just email you. I don't know.
Yeah. Email me, and then just because we don't have access to the Zoom, and then I can send to everyone. So this is really, first of all, quite a changing area, lots of investment in this space, but you can see why this is an effective tool, right? Especially as you go to the datathon, you only have 2 days, you need to rapidly prototype. We're not trying to beat the state-of-the-art model, right? We want to say, here's a question, right? You can look at the quality of embeddings themselves. You can, there's so many dimensions that you can take this for people who are in back home. You may not have, you saw how much it takes to label data sets, but if you have even 500, right now you can start to say, is this even a feasible machine learning problem with this approach, right? Yep. So, yeah.
Yeah, that's absolutely the way to think about it, is prototyping, rapid prototyping, figuring out, is this even, and we still use it. I actually find it's a much more fun to train on embeddings because you get the answer right away or within 5 or 10 minutes. Without having to launch this whole model and wait hours, days. So rapid prototyping is a huge, it may not give you something that you're going to deploy tomorrow, but it will give you a hand-wavy sense of, can I answer this question with machine learning or not?
Okay, great. I have the notebook. So thank you so much, Andrew, and hope to see you in person next year. Thank you. I'll send you a t-shirt.
Okay. Yeah. Oh, great. Thank you. Yeah.